All right, guys. I think we're getting close here. We have the secret. The secret is revealed. Just stepped away to have some lunch. Got that post-lunch clarity. We shall see. So it was kind of like this. We kind of started out with B4 is bounded by this thing with 3 zeros and this thing with 3 ones. And then we kind of like got our way up to like, all right, well, B1 is bounded by, I think it was this. It was like this -6 minus C minus 5. And then this plus 6 plus C plus 5 like this. And so the thing is like, all right, if B4 is in this range, then we're going to print out a 2. If B1 is in this range, then we're going to print out a 2. And so we start off with A. So we kind of start off with A, and we say that B1 is equal to A bit shifted over by 3. So if you just kind of think that B1 is A bit shifted over by 3. So you have B1 is A bit shifted over by 3. Yeah, and we want to come up with A. So we know that, okay, kind of maybe intuitively reasoning this out. We know that when like, so we want A. And so when we took A and bit shifted it over by 3, we know that it's between these two numbers now. So we can kind of think, all right, what's kind of like the worst case, best case kind of thing? So we took A, and if A has the form like, I don't know, a bunch of digits followed by, and like the last 3 digits are 1. See, it's kind of weird because like in this forward direction, everything is very predictable and deterministic, where we kind of start off with A, and then we bit shift it over by 3. Like we start off with A, and it's between two numbers, and it's very straightforward to say, all right, so we take A and we bit shift it over by 3, and it's still going to be between like X bit shifted over by 3 and Y bit shifted over by 3. That's like a very simple, kind of straightforward, forward kind of pass to make. But now it's kind of going the opposite direction, where we're like recovering A and recovering X and we're recovering Y. And so recall also, like, bit shifting is just division by 8 in this case. So I mean, we have that A is between these, and then we just do A divided by 8. And this is really integer division by 8. Like this is where it's a little, yeah, this is where the slight complication is coming in. that we have integer division by 8, and so we kind of have, and I just want to make sure too, like with actual values, like if we, I don't know, if we have like 1 is less than, 2 is greater than or equal to 0, you divide these things by 8, it's still going to be like, I guess like, yeah, when we integer divide these things by 8, um, now we're going to have like 0 is less than or equal to 0, which is less than or equal to 0. So it looks a bit different than this. It's still going to be, this inequality is still going to hold, but kind of recovering these differences is kind of tough. So when you divide any of these by 8, if you do like a, do this by 8. If you take a and divide it by 8, you're going to get 8 times some product thing plus a remainder. Yeah, 8 is going to go. 8 is going to go into a. A is going to go into 8. I don't know, like 8 goes into a, say, a bunch of times until it kind of can't go anymore, and then it has a remainder. And that remainder gets chopped off when you divide it by 8. So basically, like these last 3 bits with like 7, those got chopped off. So what we do know is that if like a and y, if 8 divides them the same number of times, the remainder for y, the remainder for a and y, the remainder for a has to be less than or equal to the remainder of y. So a is going to be, it's like kind of going from here to here. Like the difference between these two numbers is going to be at most, the difference of the remainders for these two numbers are going to be at most 7, I think. Like if you have like 1 is less than or equal to 2, yeah, but if you have like 7 is less than or equal to 8, then this is going to go to 0 and this is going to go to 1. No, I guess trying to think. Yeah, I guess the kind of most extreme case where difference gets introduced. So if these are all divisible by 8, that's kind of the simple case. You have like 8 is less than or equal to 16. And then if you like divide by 8, like you're good because it's just like 1 is less than or equal to 2. Like there's no error that gets introduced when you do that. But the second you start having remainders, if you have like 9 is less than or equal to, 16, then now you just have this divided by 8. You have 1 is less than or equal to 2, and kind of like the ratio between these two is different. So it kind of seems like the biggest difference would happen when one has a remainder of like, yeah, this has a remainder of like 7 and this has a remainder of like 0. Then there's basically a difference of 7 that comes in where like the difference there was like 7 numbers that were in the difference between these two, and all of a sudden that gets lost. Like, I mean, for instance, like we have 15 less than or equal to 16, and then we divide these by 8, and now we just say, yeah, or how about let's go like 7 is less than or equal to, okay, I feel like the most extreme thing would be like 7 is less than or equal to 15, because there's actually a difference of almost like 2 times r here, where yeah, if we like divide these by 8, like this goes down to 0, and this is 1. So the difference between these is just 1, but the difference between these is like a full thing of, I guess if you really wanted to highlight the biggest possible difference, like 0 and 15, like this is almost 16, but then this gets chopped down to 0 and 1. So could we write it like that? Would that be helpful? Like if we did like a plus if we did like QA, like 8 times QA plus the remainder of A is less than or equal to 8 times Q of Y plus the remainder of Y. If we kind of do that, then we divide both of these guys by 8. Where like the remainder of A is between 0 and 7. So basically the resulting number is, yeah, like this goes away and this goes away. Does it okay, so you say less than or equal to, so you basically down here, so we just have QA is less than or equal to QY. That goes away. But then we kind of like go back up in reverse, and we're like, all right, we like multiply these by 8 now. That's like the shifting to the left by 3. And like we had this whole thing was equal to A, and this whole thing was equal to Y. We want to know what A is. We want to know what A is between. we don't know what A was. Like, we don't know what the remainders are. But does it really matter? Like, what if we just say that the remainder is 0? Like, the remainder of A is 0. Like, let's just, who even cares? I mean, if we just multiply both of these by 8, the um, the inequality is still going to hold. And do we really care? I mean, our only goal is like we're just starting with a value for B4, and we want to see like a range of A's. I guess the only where it matters is like we do want the minimum. We do want the minimum A so that you'll output a B. So you'll output a 2 to the screen. So I guess the minimum A would be when the remainder is 0. Yeah, I mean, I guess that's true. I mean, like we're kind of like recovering a range of A's, and yeah, I guess it would be when A is 0, when the remainder is 0. Like that's what I feel like that's what the minimum would be. Um, yeah, the minimum would be when the remainder is 0, because like you still do need it to be like scaled up by 8. So I guess I guess like the moral of the story is that yeah, just it does feel like just doing it up by 3. I think that would give you the minimum A, and then there's also kind of like the maximum here too. We don't really care about the maximum unless maybe we do. Um, maybe the maximum would increase by 7 because we do have like the remainder that got chopped off, so we would kind of recover it, and A is like greater than or equal to this, and it's less than or equal to this. That does kind of feel like what we should do. It does kind of feel like we should add a 7 to the max side. Like, does that make sense? Where if we just said, for instance, like b is less than b is like less than or equal to 2, and it's like greater than or equal to 1. Okay, but the generative story for b is it kind of came from this like a, um, and we did integer division by 8, and we had like a y here and like an x, and we like integer divided these things by 8, and we got this. So what would be like the range for a that would be acceptable for this? If a is greater than or equal to, for this to be true, a has to be greater than or equal to maybe like the max of this guy, And like the min of this guy, the max in terms of like, this is like a remainder of 7, and this is like a remainder of 0. Yeah, I guess at this point, yeah, maybe let's experiment with it and see what we find. So, yeah, so I think just recall we've got B4, 1, 1, 1. And then we kind of like went up this chain and we got that B1 is less than or equal to, and this is like 1. Okay. And then we basically got a kind of modulo some integer division here stuff is less than or equal to let's just say like 8 times this, basically. And so C was 0. So it's basically just, like this thing minus 11. These are just numbers too. So recall, this is like 2 to the 1, 2, 3, 4. This is 2 to the 4, 16. 16 minus 11. So this is 5 times 8, which is 40. Minus 11. This is 16 plus 7, 23. 8 times 23. Wait. So this is 23 minus 11. 12. Eight times 12. So eight times 12. So 8 times 12 is 80 plus 16, 96. Basically 96. So this is saying like if A is between 40 and 96, then it will output a 2. That's basically what we're saying. We're conjecturing. So if we set A to set it to 40, C is 0, and let's just do it, I guess. Let's see. Yeah, the input. Looks like the output of 3. Just curious if we, oh wait, oh no, hold on, the input. Okay, so we output a 2. So let's see what happens if we do it to like 39. output of 5. One. Put a 0. That's not right. Go up to like 60. So we could kind of play this forward. So now that we have, I don't know, we have some intuition. I'm kind of dissatisfied by how this has kind of happened so far, but let's just see. So if we, have A and it's 40, which is, let's see, it's 32 plus 8, so 8. So we got a 2. Oh no, we don't have a 2. We don't have 1, 2, 4. We got an 8, no 16s, and 132. So this is A. So we take A and we bit shift it over by 3. So we get B1 is equal to 101. And then, so now we XOR this with 5. And recall XORing something with 5. Basically, if all the last 3 bits are set, remember 5 is equal to a 4 plus a 1. So I guess just like if these 2 bits are set, then we're going to go to 0. So it is going to go to 0 here. So we did hit the -5 thing because like these last 3 bits are 5. So now we have B3 is equal to oh wait, I failed to I guess C, it doesn't matter what C is, but C does get set by A1 and B2. So need to factor that in. So now B3, so depending on what C is, we can't just say like, oh, let's let C equal 0. So C is equal to A1 shifted over by B2. So kind of like, remember like going up this chain, we bounded B4 initially to have it to output a 2. And then we got up to B2 and we said, all right, like we bounded by this and it'll still output a 2. But now we have to, wait, where's this? I guess we go up to B3 because B3 is a function of C. So we have B4. Not X prime, but. And then B3 is. So we have that B4 is equal to B3 XORed with 6. So B3 is greater than or equal to x minus 6, y plus 6. Hmm. We just applied this like so easy, like without pretty effortless to just like say this. I feel like a very similar thing is happening in energy division, but we're getting very confused. We're getting really hung up with not just being able to do this. I mean, just kind of going like B3 Zord with 6. So we knew that, okay, B3 Zord with 6. Um, so just say that we know it's less than or equal to X or Y. And so it's almost like, okay, we have this number and like we want to get we really want to say I think I'm in the way of the stream the window. We really want to say that B3 is less than or equal to some values. We know that B3 Zord with 6 is greater than or equal to or less than or equal to. Yeah, I guess like I wasn't even really doing it intuitively before. I was just using the property of math where it's just like if you just have like an equation and you XOR something. Maybe you can't do that with inequalities though, because if you have, if you have like x is less than or equal to y, you can't just like, if you had x is equal to y, like you could multiply both sides by -1 and kind of keep this inequality. But if you have x and you multiply by -1, you have to flip the inequality sign. So I wonder if there's a similar thing with XOR where like, so say we have, say we have 5 and it's greater than or equal to, 1, it's less than or equal to 6. And then we XOR all this stuff with 3, say. Oh, dang. Yeah. This inequality might not even hold. Yeah, you can't just take the inverse and because like here's a case where it just like won't hold at all. Like if you have, so we're XORing with 3, like the last two numbers. So let's say, yeah, let's say 3 is less than or equal to, yeah, about 4, and it's less than or equal to 1. I don't know. Fine. I think this one's gonna get messed up. I think this one's gonna be good, but I think this one's gonna be bad now. So if you do 3 and you XOR it with 3, is less than or equal to 4 XORed with 3. Yeah, actually, like, forget about this side right now. If you just have this and you XOR this, you're gonna get 0 is less than or equal to this right here. You XOR this. Okay, wait. You're gonna XOR this, and that's fine. That's good. You're gonna get 1, 1, 1. So you are actually still gonna be 4, 0 is less than 7. Like that's good. But what if we had, yeah, what if we had 4 is less than or equal to 5, 6, 7? Yeah, how about that? So say we have 4 is less than or equal to 7. Then we do 4 XORed with 3 is less than or equal to 7 XORed with 3. So 4 XORed with 3. That's going to be equal to 7. But then you do 7 sword with 3. And that you're going to get 4. So now you get 7 is less than or equal to 4. And that just like destroyed the inequality. So that was kind of what a lot of our reasoning was relying on. But I think you should be able to say, you should still be able to maintain this inequality. I mean, if we shifted both of these over by, 2, shift this thing over by 2, shift this thing over by 2, then that'll hold. It'll hold. It's okay if, so you take 2 numbers, you say like blah 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 blah. This guy is less than or equal to like blah 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 0 0, and you take this thing Zord with 3 is this thing Zord with 3, and that's fine because Zor in this case is just an addition. In this case. So to kind of maintain the inequality, we could like take whatever you're zoring this with. Like if you have A is less than or equal to B, if you want to say is A zored with X less than or equal to B zored with X. This is not true in general, but if you did A times X, no, times X, no, I mean, I guess it'd be A times 2 to the X, or just like A shifted over by X is less than or equal to A shifted over by X, Zord with 3, well, Zord with X is less than or equal to B shifted over by X, Zord with X. That's true. This kind of looks familiar to what we were doing before, but maybe let's stick with the end of this thing here. Like we have like B4 has to be less than or equal to some, B4 has to be less than or equal to some value. And then we say that B4 is equal to B3 Zord with 6. So we want B3 though. we want to say, like, we want to get so that B3 is greater than or equal to some value, so less than or equal to some value. And we want this bound to be tight too. Like, we don't just want B3 to be greater than or equal to some number. Like, we could just say it's greater than 0. But we want it to be tight. I mean, we could look at it with real numbers. Like, we know that B4, like, we do want it to be less than or equal to 10111. And then we have B3 XOR with 6 is less than or equal to what is 6 again? 6 is 4, 2, 1. So we want to get a bound on 3 now, B3. What number, when you XOR it with 6, will give you this exactly? Like, if you do 10101 and you XOR it with 6, then you're gonna get this. So, okay. And then what number, when you XOR it with 6, are you gonna get this? So it's like no, would it be 010 basically? XORed with 6, yeah. So if it's like 10, this thing XORed with 6, you're gonna get this 10101. Wait, no, 10111. Yeah. So if B3, this is kind of Y and this is kind of X. This is, if B3 is like greater than or equal to the, I want to say if it's greater than or equal to this, or it's less than or equal to this, but I don't know if you can say that about it, because like you're going to be increasing these numbers, and XOR will just kind of like flip them. Like, okay, what if we said, so hence B3 is greater than or equal to, yeah, this is totally like nonsensical, because I want to say it's greater than or equal to this and less than or equal to this, but this number is greater than this number here. So yeah, this is just totally fucked. When you take when you take a XOR thing, like, you just you just kind of like lose it's like the inequality just gets like completely like fucked, gets completely scrambled. Unless you do like bit shifting kind of trickery to prevent that from happening. What if something's jumping out to me now? Like what if we just kept replacing this by this by this by this? So we just get this like big expression that's just like, oh, the result, if the result of this computation is less than or equal to this. Yeah, that's not the most useful. See, now I don't know if we're going to be able to say like, because Zor kind of like scrambles everything up. I don't even know if we're going to be able to say like a is greater than or equal to some value and less than or equal to some value, and C is like, you know, and then hence, 2 gets output. I don't know if we're going to be able to say that. We might have to say something more discrete, like if A is in like this set, that's not necessarily just like a consecutive sequential set of numbers, and B and C is in this. It's almost like we might just have to have like kind of like this A cross C set where we have like settings of A and B, A and C that give us 2, and those don't have more structure than they're just pairs of numbers. Yeah, so I feel like this approach was probably pretty ill-fated, misguided to like try out, because these inequalities kind of get destroyed. Can't really necessarily isolate B3. Maybe a better approach is to kind of go top down and see if we can just kind of like eyeball the value of A that we need for this to work. So we take like B1, and so we take A and we bit shift it over by 3. And yeah, see, now it's kind of occurring to me when I was like outputting those numbers, when I was testing them out, it's like where like 40 worked and then 41 didn't work and then like 42 worked. Yeah, I don't think you're gonna be able to find a range of numbers like that. It's just some like non-contiguous set of numbers that would give you that potentially. So we do A divided by A bit shifted by 3, and then B2 is B1 XORed with 5. C1 is equal to A by B to the B2. Six. A and B. So just to kind of draw out the dependency like flow chart a little bit, it's like kind of start with A. So we do this B thing, kind of like A, B, and C. Yeah. And it's kind of like A just goes into B1, and then B2 is just a function of B1, and then the next value for C is a function of A and B2. C1 and B3. Maybe it's better to do it kind of like down here, where we get kind of like C1 and A also. It's required for that. And then B3 is like this. And then B4 is just a function of this. And then it's like out to the screen. Maybe to see this a little bit more sequentially is just, it's like a little bit further down here. C1. We get C1. And that's and then B3 is B2 and C. And then B4 is this. So that's kind of the steps. It's like this is step 1, this is step 2, this is step 3, step 4, step 5. Okay. If it would be helpful at all to write out the operations too. It's like have kind of like A, it's like A and B, C. So do B1, B1, this is A, bit shifts it over by 3. It's the operation. And then B2 is B1, XORed with 5. Then C1 is A and B2. Basically this kind of thing. It's basically like this kind of thing. And then B3 is B2 and C1. The XOR. I guess it's this like XOR kind of thing. B3. And then B4. Okay, I'm like down here below the my thing's in the way. but then you just like XOR with 6. Yeah. So I can kind of see it. I don't know if it's super useful to see that. I guess the most useful thing is just to see the dependencies. Hmm. Where do we go now? Maybe that thing that we were saying before, where we're kind of going backwards, where it was like, it's like B4 is less than or equal to, like, to print out 2 is this, and then it's equal to B3 stored with 6. Yeah, less than or equal to. So now we're saying, like, for what values of B3, when we XOR it with 6, will be in this range? What values? I mean, we could find the set of values, and then we could take we could take like the minimum value there and the maximum value, but then like there might be discontinuities in here. So I guess we do have to kind of like just take a set, but we can be like, all right, B3 has to be like in the set, like this thing. It's almost like a breadth first search kind of thing where you just kind of have to like expand each of these. Basically, you say almost like, what is the inverse of this? And like the set is just kind of expanding. It's kind of similar here. I mean, this is a set of numbers, but they're just all continuous. So that's kind of interesting. So it's like if B3 is in this set, then B3 XORed with 6 is in this range. I mean, yeah, if we just want to brute force it, we would just iterate over all these numbers, like from like I up to J. We would say, all right, like B3 XORed with 6 is equal to like this number here. So we're saying, okay, like what value of B3 when you XOR it with 6 is going to get this? So we could just, this is going to be 0, and XOR this with 6. So we can basically get all the possible values for B3. Get all the possible values for B3 by looping over from I to J, from like this to this. We just XOR all those values. And so we say that like B3 has to be in this set for us to get a 2. These are all the possible values for B3 that'll give us a 2. And then once we have that, we're like, all right, if B3 is in this set, then it'll do is this. But like, what is B3? B3 is B2 XORed with C1 B3. So just kind of just with the notation, the math notation is in this set thing. So now we say if B2 XORed with C is in this set, then like that implies that like the screen gets a output of 2, basically. So now do we just like loop through all these elements and say, all right, well, what value when you XOR it with C will give you a, like the first element and the second element and the second element. So then I guess you just go through all these and just like XOR them with C. And then you basically get, B2 is in this set. Then you have B2. So then you like XOR them all with 5. And then you get B1 is equal to this set. B2. And then you say, all right, so if B2 is any one of these, then we will output a 2 to the screen. B2 is equal to A1 bit shifted by 3. So then we say, if A1 bit shifted by 3 is any one of these numbers, then okay, if A1 bit shifted by any one of these 3 numbers is, if A1 bit shifted by 3 is any one of these numbers, then we will output a 2 to the screen. So here's where it gets a little like expansive, to where we have for each of these numbers, we're gonna get maybe kind of like a little branching of numbers, because if we've got the number in here, just 1, then what numbers, when you bit shift it by 3, will give you 1? Well, like 1000 will do that. 1, 001, 1010, 1011, 1100, 1101, 1111, all these. So these are going to branch out to a factor of 7 each time. And then we're going to get, and then we would get, like A. The values of A is going to be in here. So then it's like, all right, if A is any one of these numbers, then we will print out a 2 to the screen. Okay. Now the kind of like dirty thing that we elided over was this step here. We said this thing XORed with C. This thing's XORed with C. So C is a bit, I mean, we could just fix C, I guess. Maybe let's just like assume that C is 0 in this case. So if it's 0, so we say like this number is XORed with 0 is in here, then you're good. So at least for this first thing, like maybe we need to be careful with C once we're trying to like output this for this entire program where we have to go multiple times. But just in this simplified case, let's just say let's just say C is 0. So this is pretty cool. I think I think this is a good thing to get us a little unstuck. And let's see if we can get anywhere with it. It's kind of like, maybe I'll just keep this. Yeah, just like keep this right here for now. Let's see if we can actually code this up a little bit. I almost want to make this just like a standalone program right now. So basically, yeah, we're starting with B4, and we say if B4 is any one of these numbers. So maybe we could like just define B4 is we said that if B4 is greater than or equal to 1, 0, and is less than or equal to 1, 0, 1, 1, 1. And this was 2 to the 1, 2, 3, 4. This was 16. And so this is 16 plus 7, right? 23. So from 17 up to 23. So it's basically a range of 16 up to 23 plus 1. And we'll just take a list of that. That's fine. Just keep it as range because we're going to loop over. So basically, let's just, we can freaking verify this at every step. I actually think a Jupyter Notebook might be better for this. Like if we, yeah, let's see. So, yeah, about this, yeah. Instead of the terminal, we can have this here. So we can be like, yeah, we could just, can save this here. Let's mark down. Do that. So we can start off with B4, and it's equal to the range of 16, 23 plus 1. Let's say B4. Yeah, fine. Just keep it here. All right. So, okay. Yeah, maybe I don't. Maybe it's just cool to keep the terminal. That's fine. Just keep it there. Maybe. I don't know. Maybe I'll look at here. All right. So, all right. And we can test this out at every step. We can say, all right, so for B4 in, let's do B4 3. This is how you do it in Python, right? Yeah, just print this out. And yeah, we get a 2 every time. So that looks good. What if we did, and let's just check like one above this. Let's check like 25. We shifted over by 3. What do we get? We get a 3. And one below this, 15. Yeah, we got a 1. So cool. Yeah. Kind of, yeah, verify this at every step. That's pretty cool. So now we say, all right, so now we're like, we have these numbers for B4. So we know that if B4 is in, this set, then we're going to get a 2. And we know that B4 is equal to B3 XORed with 6. So if B3 XORed with 6 is in this set, then we're going to get a 2. So we want all the numbers B3 such that when you XOR them with 6, you're going to get a number in this set. So that's just all the numbers in the set XORed with 6. So let's do that. B4 XORed with 6. Okay. This is B3, like the set, basically. And see, and this is interesting too, because 16, 17, 18, 19, 20, 21, 22, 23. Okay, so it is a range, like, and it's a contiguous range too. I guess that kind of makes sense because well, so okay, it's they just got kind of jumbled up. We're like almost not 18, 19, 16, 17, 22, 23, 20, 21, 18, 19. That's really weird. Like it's almost like a rotation, like a ROT 13 kind of thing. But so yeah, if we take all the B3s and we say, all right, for B3 in B3, if we take each of those and we say, all right, B4 is equal to B3 shifted over by 3, and then we print B4, we're going to get 2s. Okay, that's good. Maybe we can go kind of up. Yeah, this is pretty cool. So now we have this set B3, and we're like, all right. So now we have, yeah. So now we know if B3 is in any, if B3 is in the set, then a 2 is going to be output. Well, what is B3? B3 is equal to B2 XORed with C. So we're going to XOR every number. So now to get all the B2 that'll output to, we can we can XOR it with C. Yeah, let's just say C is equal to 0. So we'll say for B3, B3 XORed with C, and this is going to be equal to B2 now. So we got that. So now let's just say for B2 in this. So how do we get B3? We do B2 XORed with C. This is B3. and then B4 is equal to B3 XORed with 6. And let's print, and then wait, this is fucked up. Okay, so B4 is any of these values. Kind of mess this up here. So B4 is equal to B3 XORed with 6. and then we want to print out before. Yeah, okay. Okay. So now, yeah, B4 is equal to B3 XORed with 6. Now let's print out B4. Yeah. So there we go. We get 2s again. B4. Just to be consistent, let's print. All right, so we get 2s, we get 2s, we get 2s. So now we're going up. So getting there. So now we got B2. So we say, all right, if B2 is in this set here, then we're going to output a 2. And we have that B2 is equal to B1 XORed with 5. So if B1 XORed with 5 is in this set, then you're going to output a 2. So we actually want to get the values of B1. So we want to get all the values. So we want to get all the values such that when you XOR it with a value, XOR it with 5, you get a number in this set. So yeah, I don't know. You're just kind of, yeah. So for B2 and B2 XOR with 5. This is B1. So for B1 in B1, we're going to basically say B2 is equal to B1 XORed with 5, and then basically just copy the rest of this stuff. We get 2s. So is this the last thing? So now we say, all right, if B1 is in this set, then you're going to output a 2. And we know that B1 is equal to A1 bit shifted by 3. So if A1 bit shifted by 3 is in this set, then we're going to output a 2. So we want to find all the values A1 such that when you bit shift them by 3, you're going to get an element in the set. And those are all the values of A that'll output a 2. So all the elements A such that when you bit shift them by 3, you're going to get a 2. So we have B1. So all the elements such that when you bit shift them by 3, you're going to get a 19. So how do you do that? Let's just look at 16, for instance. 2 to the 4, right? So it's 1, 2, 3, 4. So all the numbers such that when you shift it over by 3, you're going to get this number. So it's basically this number plus all the combinations, permutations of this, I guess. So we basically take this, we shift it by 3 over this way, and then for I in range 0 up to 8, we would just do like that number plus I and like append that, I guess. So kind of like for B1. Now let's take the number. I don't even know if it's like let's say B1 shifted over by 3. So for I in range up to 8. So we're filling up A basically. And so we say this, it's shifted by 3 plus I. I guess this is going to be like an element of A here. And let's say A dot append A. And I feel like that should work. So all these numbers, yeah, we'll give you 2. We are alleging. So we have A, and so we'll just say for A in A, we'll say B1 is equal to A, but shifted over by 3, and then we'll just get the rest of this program. And we should get all 2s, but we don't. So what happened? Oh, I wonder if this, no, this shouldn't, there's no way. Oh my God, I guess like this bit shifting thing has crazy low precedence. I assume that it would have the highest precedence for some reason. Okay, interesting. All right, but yeah, so I guess these are it's kind of alleging that these are all the values. It's crazy, yeah. So we do actually get so we do still have a range. Like we still do have a contiguous range. So there's hope that we can actually bound it. It's kind of interesting, I guess. Could do some kind of okay, so we can kind of test this out a little bit too. We can kind of verify this, like kind of, not 100%, but let's say, so basically this is 128 up to, so let's go from to 256 for A in range 256. Let's do this and let's just verify that. Okay, I guess all those numbers, okay, we print 0, 1, and 2, and that's kind of it. Okay. So that's looking good. There's no discontinuities or whatever. Yeah, let's just take one close kind of look at this here where recall kind of, okay, so with our the newfound intuition of kind of going backwards with saying, okay, we want kind of like consider it case by case, number by number. If we know that B4 is greater than or equal to 1 like this, then, and B4 is equal to B3 XORed with, oh, dang. Sorry, I was writing over the my video there. And we have that B3, B4 is equal to B3 XORed with 6. Then what can you say? So kind of using this here, I'll bump this up. So you basically said, yeah, so kind of going with our intuition here that we just gained. So if B4 is in this range, then we will print a 2 out to the screen. So like if B4 is in this set here, you can think of it. And we know that B4 is equal to B3 XORed with 6. So if B4 is in this set, then we'll output a 2. If B3 XORed with 6 is in this set here, then we will output a 2. So what are all the numbers B3 such that when you XOR them with 6, you're going to get a number here. And so you're just going to go like through each of these numbers and XOR them with 6. And so that's all the numbers B3. So yeah, I mean, I guess like the lowest it's almost like this number minus 6 and then this number plus 6. That's like the biggest absolute range, but you need to well you actually don't know. You just have to because you kind of go up and you kind of like march through this this list, and you get something that's like bigger, you get something that's increasing, and then you get something that's smaller, like 2 3, you get like 4 5 2 3, something like that. So you kind of need to check the values in the left side of this range kind of, and the values in the right side of this range. And so like let's do that. Let's check the leftmost value. So if you XOR it with 6, so you're gonna get a 1. Okay, so now what if you XOR the next value with 6? Like 10001, XOR it with 6, you're gonna get 100. So you're gonna get a smaller value than that. But you're never going to get, here we go. You're never going to get a smaller value than this because XOR is never going to drop you. XOR is never going to drop you below this. But is that a tight lower bound? Probably not. Yeah, because you're never going to get, well, you will get all zeros actually, because yeah, you're kind of just marching, you're kind of just like incrementing this thing up to be like all ones. So you are going to get to a point where you're like 10101, and then you're going to XOR it with 6, and then you're going to get 10000 like that. And so you are going to get that value there. So you basically will get B3 is greater than or equal to this value. And what's the biggest value in with these elements in between this thing? Well, this is the big, yeah, because when you do 10010 and you XOR this thing with 6, you are going to get 10111. So that upper bound does kind of remain there. So when you're kind of doing it with this range kind of thing, you can kind of reason that, I mean, because this is the biggest value, you're never going to go above that. Like XORing this value with 6 is not going to like add 6. It's going to subtract. It's going to subtract this thing and this thing. So it's going to subtract 4 and 1. It's going to do a -5, but there will be a lower value, which will bump you up. So yeah. So this is cool. I would consider this a breakthrough on this problem. So we're really getting somewhere with it. And yeah, we will continue it next time. This is great. Okay. See you guys. Peace.